Okay, we're going to show that area can be computed using Green's theorem, which is unsurprising because if in the 1D case, we know that the length of a line segment is definitely the same thing as the integral from a to b, and we know this is x evaluated from a to b. So this we know that the zero-dimensional quantity here, it actually corresponds to that one-dimensional volume, area, length type quantity b minus a. So actually in 2D, we know that the area of a region R bounded by a curve C, closed curve C, we know that the area is actually this expression. It's a line integral. It's actually any of x dy or y dx with a negative sign in front of the y, or the average of these two things. So half of x dy minus y dx. You can use any of these to compute the area. So why is this true? So if we put P, Q equal to each of these things in turn, we can see that it has to be true. So for example, in the case 1, we know that at P equals 0 and Q equals x, and so Qx equals 1, Py equals 0, so we end up just getting 1. So we take that integral with Green's theorem, and we just get a. On the other hand, in the second case, where P is now minus y and Q is 0, we get Qx minus Py equals 1 again. And of course, the average of something true is also true in this case. So let's do an example of this, because it's actually kind of useful for computing difficult areas. So let's find the area under one arch of the cycloid given parametrically by t minus sine 2t, 2t in front of that first term, and y equals 1 minus cosine of 2t. And we'll actually need to find the range of t given by this one arch condition here. So I'm not going to try to draw a cycloid y as a function of x, but I can certainly do y as a function of t. Let me just quickly draw cosine for those of you who would like a refresher. And here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi. So now if I do, that's cosine. So now if I do 1 minus cosine t, then, well, this is 1. Remember, this is negative 1. So what happens if I take 1 minus this, we start out at 0, we end up at 1, and we cap off at 2. And then I'm just going to reflect this back over. Not drawn to scale. So this is 1 minus cosine t, and to get 2t, I'm just going to speed this up. So I'm going to draw the exact same thing, and I'm just going to relabel. So here's pi instead of 2 pi. Here's pi over 2 instead of pi. And this is now 1 minus cosine of 2t. Okay, so this is one arch. One arch is the range t goes from 0 to pi. Right? Because as soon as we draw more, we get more arches. So that's all we need to do. Now, let's see if we can apply Green's theorem. We need to know if it's a plus-oriented or a negative oriented. So if we have a plus orientation, we're okay. If we have a negative orientation, then we just need to add a minus sign. So how do we do this? So we compute we'll compute the tangent vector of the curve to see where it points. So the tangent vector is just the derivative. So it's just x prime and y prime. And then we look at this vector, x prime, y prime, and we see where this thing is pointing. Okay, so let's differentiate. We get 2 minus 2 cosine, and we get 2 sine of 2t. Now notice that these things are always positive in our range, right? Oh, well, I guess y prime is negative. But it looks like, yeah, it looks like x prime is positive all the time. So that means if I draw if I'm going to draw tangent vectors at the critical points, so the x is always positive, right? But the y will be positive for small t. If you have small 2t is less than pi. On the other hand, if 2t is greater than pi, the y will be negative, so now we have to switch it. Notice this is now this has the negative orientation. It's clockwise. Okay, so we just need to add that minus sign. So what I did was, remember, just to recap, what I did was I plotted the tangent vectors of this curve. Not of this one, but of the cycloid, and I'm just overlaying it on the graph to see what's kind of going on. Okay, so now that we got that out of the way, to get the area, we'll add a negative sign to 1/2 x dy minus y dx. And I'm using the symmetric form. It turns out this one is easier than x dy or y dx alone. So, and you'll see why. So we just need to compute these differentials. So compute, let's just recall the x is t minus sine 2t, so dx will be 2 minus 2 cosine 2t with a dt outside. I'm just going to factor that and call this c. So y will be, of course, 2 sine 2t. So dy will be 4. Oh, I'm sorry. Y is 1 minus cosine 2t. I just wrote down the derivative. Well, that makes it a little easier. So 2 sine 2t, I'm going to relabel that as 2s. So it makes the algebra easier. Right, because we need to multiply some stuff. So x dy minus y dx divided by 2, it will now be 2t minus s times 2s dt divided by 2, now minus 2s times dx, I'm sorry, 1 minus c, that's y, times dx, which is 2 times 1 minus c dt, all over 2. So let's cancel these 2's here. And so we end up getting a dt on the outside. And on the inside, we'll have 2ts minus s squared minus 1 minus 2c plus c squared. That's the 1 minus c squared that we had here. So looks like we have this -1 plus 2c minus c squared. And I'm going to group together this to give me a 1, because sine squared plus cosine squared is 1. And this one will combine with this one here. So we end up, after all of this, with 2ts minus 2 plus 2c. Phew. So that gives us that differential expression. And one subtle point that I kind of glossed over was we just looked at the arch part of the curve. We looked at the curvy part. It turns out there's also this part here, the lower base part. This does not contribute. So let me just explain really quickly why that does not contribute. So here, this is the curve y equals 0, and x equals t ranging from, let's say, pi to 0. So x dy is x d0, and y dx is 0 dx. So there is no contribution to the line integral from this. So with that out of the way, let us integrate this last differential that we've computed. So the area is now the integral from 0 to pi of 2ts minus 2 plus 2c dt. And I think it's a good idea to put the arguments back in, because we will see that one term actually disappears. It is this last term because of cancellation. I'm just going to quickly draw cosine, and you'll see what I mean. So with that done, we see that this -2, it will integrate to -2 pi. Oh, and we forgot our orientation. So I just added a minus sign in front, just so we are doing things correctly. So this -2 pi will turn into a positive 2 pi at the end, which is good because the area is positive. So let's integrate this thing. I'm going to use integration by parts and do this really quickly because you should know all this already. So this will give me a t cosine 2t evaluated from 0 to pi, and then we'll have I'm sorry, this is a negative sign, so there's a plus. Integral of cosine 2t. There's no t here now because we differentiated that. And we already know from cancellation this goes to 0. So let's do this pointwise term. And we know that 0, it'll interact well with that t, so we just have the upper limit. So it's negative pi cosine 2 pi, so that's 1. So we just get negative pi. So therefore, area will then be pi plus 2 pi. So we should just get 3 pi, if I didn't make an error. This last part is the least important, and on any exam that I grade, I would certainly count this the least. I think setting everything up before this and getting to this differential, I think this is the most important part. So I hope this was helpful. Thanks for watching.